Hi everyone. In this tutorial, I will show everyone how to simulate the radar cross-section, specifically the monostatic radar cross-section. So using CST. So here's the CST software. So first we need to go through this new template. And we need to choose microwave and RF/optical. And right here, we select radar application. Next. And we select the first one, monostatic radar cross-section. Next. Depending on the object. So in this tutorial, I'm gonna select small object because I'm only gonna simulate the RCS for a small dipole as an example. So here you can choose whether you're gonna use frequency domain solver or time domain solver. I prefer use integral equation frequency domain solver because we can see the radar cross section for the frequency. Here you can define the unit. Say we want to design a dipole at 2.4 gigahertz. And then in the setting, let's say we want to design a dipole at 2.3 gigahertz. So we can define the frequency mean max. And then make sure in a monitor we check far field because we can only simulate RCS in the far field monitor. Next. Yeah, and it will try to create a template, which is okay. Finish. All right. So first thing I do is if you can go to the ribbon and view, come over to select view. The typical perspective is the y-axis pointing to the north or pointing up. This is when we simulate RCS. This is going to be not going to be convenient. So I will prefer to do ZX up. Later, you're going to see that we will rely on the this spherical coordinate that has the axis pointing up, x pointing us, and y pointing to the right. All right. So in this document, you can see there are three predefined variables: alpha, theta, and phi. Let's go ahead and make a dipole first. Just define some random variable because it does not matter for our purpose. All right, so we have the first leg. We can define another leg right here. Oops. Oh, 0.5. All right. So here is our dipole, and the material is PEC. So now with the dipole, first we need to go to the ribbon simulation. We double check the frequency of the solving, 2.2 to 2.4 gigahertz. Background, we can do it as everything as default. So material type is normal. We don't have multi-layer. It's just a dipole. We can apply the surrounding padding or space in all direction. Boundary setting, we don't have to do this because since it's a very simple dipole, make sure it's open so that the boundary will absorb the phase, the propagation. Fractional wavelengths, usually quarter wavelengths is good enough. Good trade-off between accuracy and simulation time. And for this one at frequency, I usually prefer to center and monitor. So it will consider the lowest frequency, which will increase the wavelength and increase the boundary box. Okay. And then mesh setting. Depending on how fine we want to parse the object. So usually we need to look at it and have a very good general sense about what a good meshing is. So let's say 50-50. And then we update the mesh view and we can look at it. Seems pretty okay to me. The more mesh, the longer time it take. But the accuracy, there's a threshold. Upon a certain mesh setting, the accuracy won't be improved. So you will need to figure out the best global property of the mesh for your object. And you can also see if you move your cursor, if you hop your cursor right here, you can see the min and max quality and the average quality. Seems pretty bad actually, but not really sure why. Visually seems okay. Okay, close it. And now for RCS simulation, because we use a template, it gives us a plane wave already. So this is assuming the dipole or the object is in the far field. And so the radiated wave toward the dipole is already a plane wave. And we can set where the incident wave is coming from using those parameters. So come back to here again. You see the variable theta and phi. That's exactly the theta angle and the phi angle right here. So for now, over theta equal to 0 and phi equal to 0, that means we're at the North Pole, or we're at the Z looking. We're at the Z location and looking toward the negative Z, which is why we have the plane wave right here. Let's say now we want to we keep the phi equal to 0 and set the theta equal to 90. In that case, we should be locating at the positive x-axis and looking at the negative axis, which meaning the incident wave should be propagating toward the negative x. So let's try that. So phi equal to 0, theta equal to 90. And then we update. There you go. And if let's say now we want our incident wave is coming from positive y and propagate toward negative y. So that in that case, we will need to change our phi from 0 to 90. So 90, update. Here you go. So by adjusting the theta and phi, we can change the incident wave angle. So for this tutorial, let's say we want the theta equal to 90 and phi equal to 0. Now what is alpha? Alpha is how this orientate or how the E field rotate with respect to the x-axis. It has a description right here. I'm gonna adjust the table so you can see it. Rotate angle of E field vector relative to x-axis. So let's say now we instead of the E field polarization toward the negative Z, we want the polarization toward positive Z. So we want to then we can set the alpha equal to 180 and update. See, it rotate. And here's a better animation. So if we can animate the parameter from 0 to 190 with step size is equal to 10, so it will show you how the E field rotates from 0 to 10 to 20 all the way to 180. Let's try it. Okay. Just like this. All right. So this is over incident wave setting, the orientation. And now, how do we start the simulation? So first, we come over to here. Sorry, actually. So first, we check the field monitor. If we only want to know the RCS at one frequency, then we don't have to bother to simulate two other. But if we want to simulate RCS at a defined frequency, then let's say you want to simulate RCS of 2.2, 2.3, and 2.4 gigahertz, then you have the setting. Otherwise, if you have any other setting, you go to the simulation in a ribbon, and you come over to field monitor, and then you can define more frequency monitor right here. So check the far field / RCS, and then you can individually put the frequency of interest, or you can set the step size or sample. So let's say right now I'm interested in between 2.2 to 2.4 with a step size equal to 0.02 gigahertz. Then you can click OK. Then here you go. You're having more frequency field monitor right now. The more field monitor you have, the longer time you take. So this is really up to you. For this tutorial purpose, let's only simulate 3 frequency points, just 2.2 and 2.3 and 2.4. Then coming over to home and setup solver, everything is default. It's okay. And then the important part is monostatic RCS sweep. Check this and click property. You have two settings that you need to set: incident field setting and observation angle sweep. Incident field setting, so we just set the orientation. Now we just need to set the amplitude. So add. So you have 5 different options: horizontal, vertical, left circular polarized, right circular polarized, and custom. The name is actually pretty bad, but what it actually mean is, let's say for this vertical, in our case, remember we have phi equal to 0 and theta equal to 90, and then what we're actually setting right now is the theta component and phi component of the E field. So so think about in our propagation orientation setting, our theta is actually our theta is vertical, which is pointing toward the North Pole or the Z-axis, and our phi is the horizontal component, which is pointing toward the minus y direction. So what we want to, depending on how you want to observe it, usually you want the theta component, or you want the component, you want to define the amplitude to be exactly the same as your E or polarization. So in our case, our E polarization is pointing towards the Z-axis, which is aligned with the theta component of the E. So we want to set the vertical to be, we want to set the vertical and 1. That's it. For other setting, let's say if you want to set the horizontal, so that will set the phi component of the E field. Because the phi component of the E field is orthogonal to the E orientation, then your RCS is going to be a very small number, or almost just noise. So just be careful. Left-hand circular polarized. In that case, you will set the both the theta and theta. You will set both theta and phi component of your E field. And if you click OK, you're gonna see is 0.7 and minus 0.7, meaning in your case, you're having the theta component is 0.7 amplitude, and your phi component is minus 0.7, and their amplitude, their total amplitude is a square root of 0.7 squared plus minus 0.7 squared, and that's equal to 1. Same thing as the right-handed. It just you only change the phi component. Okay, so for our case, we set the vertical, which is we only want to set the theta component of the E field, which is aligned with our E orientation. Then the observation angle sweep. This is where you can set how you want to observe your RCS. For monostatic, your incident field is the same. You want to observe your the backscatter signal that is exactly at the incident field orientation because it's monostatic. That's how it defined. So for this one, it does not really make a lot of sense for doing any sort of sweep. You can either do single point, which is, I think this is going to be very important already. Like this is going to be already pretty useful. For you, we're going to set theta equal to 90 and phi equal to 0, meaning our observation point is also on the positive plus x axis. And then you can set OK. Otherwise, you can also just set it to be some sort of sweep. Say you want to sweep theta for phi equal to 90. So you can do this. So this just means that you're setting phi equal to 0, and then you are sweeping the theta from 0 degree all the way to 180, which is from positive z-axis, and along with the xz plane, you sweep from positive z-axis, then all the way to the negative z axis. And remember, only at the phi equal to 0 and theta equal to 90, only at that point makes sense because we are setting the monostatic RCS. Click OK. Now we should be ready, and we can click Start. All right, now it's done, and then you can see in the far field result, you're gonna see the monostatic result for each frequency. So we select Cartesian, and you can see that at 2.2, 2.3, and 2.4, we have different RCS in absolute value. You also see this 3. They don't make any sense because that's bistatic scattering RCS, but we didn't really set anything for the bistatic. So these 3 does not make any sense. So please focus on the longer name, the name that when you click in, you're gonna see the title, that is monostatic RCS. This is absolute value in the log scale. You can see you can check the linear scale, which is only meter square. You can also check theta component or phi component, the magnitude, and the phase. So again, what it means is, remember, we observed at phi equal to 0, theta equal to 90, and because the E field has 2 components, the theta component and the phi component, So when we observe the backscatter signal, we actually observe both the phase and the magnitude. Usually we only care about the magnitude, just like we're observing a fighter jet, and we want to know how big it is on a radar, and then that's the magnitude. We usually don't really care about the phase, but just in case you are, then you have the option to see what the phase looks like um, for the theta component, and what the phase looks like of the phi component, and you can do it. So now there's another thing that we have the RCS result for 3 different frequency. How can we plot the result to the same? How can we change the axis to the frequency and the y-axis to the RCS result? So for that, we need to go to post-processing and then result template. So here, the first drop-down menu should be far field and antenna property. Usually that's the setting by default. Second drop-down menu, we want to look for the far field result. Here it's going to pop up a window like this, and then we want to select nothing but O settings right here. So here you're going to see so many options, but there's only a couple options that we're interested. First, we want to browse the result. We want to select any of the longer name. Remember, the longer name is correspond to the monostatic. The short name correspond to the bistatic. So any of the longer name is okay. Click OK. And then in the second one, we want to select broadband set frequency. So we have 2.2 from 2.2 to 2.4 gigahertz, and our step size is 0.1. You want to go larger than what you saw than smaller, because the finer step size does not make sense. You didn't simulate, so it does not make sense. Usually, what I do is just I set it to exactly the same as my the field monitor that I set it. Okay, and then your evaluation range. Remember, for our case, the only meaningful observation angle is at theta equal to 0 and theta equal to 980. So let's just set single direction. So in that case, for each frequency, we are only getting one RCS result. This is less complex, more simple. Then to the right, you're going to see this directivity. We change it to RCS square meters. And then plot mode, very important, very important. But have to make sure is you select linear scaling, because for some reason the CST does not convert meter square to dB meter square properly. So make sure you check linear scaling, and later you can use MATLAB, Python, or whatever to convert the linear to dB. Then reference distance. So we usually observe the backscatter signal from a distance. Just make sure this is a far field distance, which is at least 3 wavelengths from the object. So for 2.3 gigahertz wavelength, the 1 meter is almost 10 wavelengths, which is okay. So click OK. And then the second important option is right here. You can either select absolute value of the RCS, or if you're only interested in the theta component, or if you're only interested in the phi component of the RCS, you can select. Or sometimes if you're only interested in the phase, you can also do it too. So let's say we're only interested in the absolute value. Then you select absolute value and you click OK. And here you go. And then you evaluate, and you have the result. See, we only have 2.2, 2.3, and 2.4. That's why you have the data point right here. And these are just interpolation, which is actually just connect between those two dots. And you have the result. with horizontal axis is frequency, and vertical axis is the meter square. So that's it. And as a sanity check, remember I mentioned the phi does not make any because we set over theta the theta component of the E field. So the phi does not make any sense. So you can see right here, if I check the absolute value of the RCS is something like this. The maximum point is 48 negative 38.7 dB meter square. You check the theta, that's exactly the same thing. But if you check phi, negative 150 dB meter square, almost just noise, does not make any sense. So you can also sanity check to coming over to the solver setting property of the RCS, and you can change the amplitude to horizontal, meaning you're setting the phi component of the E field. And the phi component, remember, is orthogonal to the E field orientation. And then if you run a simulation, I'm going to wait until we finish. But if you run a simulation, you're going to see that the absolute value of the RCS is basically just noise, because you set the amplitude of the E field that is orthogonal to its actual orientation. So in that case, it does not, the calculation will just be it's basically just going to be 0. All right, so the simulation is done. Check the result. Oh, I see the error. Okay, we can fix the error later. But you see right here, the absolute value is basically just negative 81 dB. Make no sense. And theta component is basically just also huge error. We're not error, like a very small value. And absolute value aligning with the phi magnitude. And then the error came from post-processing the result template. Basically, it's just telling us to reevaluate. Well, basically, I think it means it does not make sense to do this. Let's try it anyway. Okay, there you go. Yeah, that's how you simulate RCS.